Welcome to the Explainer. Today, we're putting on our aprons, grabbing our spatulas, and stepping right into the academic kitchen. We're going to explore the ultimate recipe for mastering one of the absolute most notoriously challenging topics in the entire Cambridge physics syllabus: current voltage characteristics. We're talking about completely deconstructing those tricky IV graphs for a resistor of constant resistance, a filament lamp, and a diode. Think of this like a high-end cooking show. To get a Michelin star, or in our case, an A star, you need the right ingredients, which is your evidence. You need the cooking process, which is your analysis, and you need the final plating, which is your evaluation. Whether you are currently studying syllabus 0625, 0651, 0652, 5054, or even if you're looking ahead to 9702, the framework we are exploring today is literally the blueprint for success. We aren't just guessing here. We'll be looking directly at what senior examiners and subject specialists actually demand from top-tier candidates. So let's dive into the material and start cooking up that perfect response.
It's a fascinating question, isn't it? What actually separates a solid B grade from an outstanding top-of-the-class A star in physics? To really understand this, the source material presents a super helpful comparison through two hypothetical students. Let's call them Alex and Sam. Now, Alex is the kind of student who walks into the exam hall and completely overloads every single answer with raw, memorized physics facts. If a question asks to explain a filament lamp graph, Alex just dumps every single fact about electricity onto the page. There's no real structure, just a massive wall of text. They're throwing everything at the wall and hoping something sticks. Then you have Sam. Sam is the rusher. Sam sees an IV graph, completely misses the specific command word in the prompt, and just writes a really generic rushed response. Sam might see the word explain, but actually writes a describe answer. If you were to look at their papers, you'd just see red pen marks everywhere. Both of these approaches completely miss out on top marks. Why? Because the core insight we've gained from examiners is that the highest level isn't about how much raw data you can cram into your brain. It is all about analytical depth. It's about proving, beyond a shadow of a doubt, that you can logically connect the evidence you see on the page to the fundamental physics principles. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the masterclass roadmap we are using to decode the syllabus today. First, the exam mastery gap. Second, core IV graph principles. Third, the procedural framework. Fourth, principal examiner warnings. And finally, critical evaluation skills. Let's get moving. Section 1. The exam mastery gap. This right here is where the source material indicates so many incredibly smart, well-prepared students stumble. They fall right into the gap. You might spend months, literally months, memorizing the exact shape of the IV curve for a diode. You can draw it in your sleep. But when you get into the exam hall, the adrenaline kicks in and you rush through the command words. You don't have a structured strategy to translate your knowledge into the specific format the examiner is begging for. Look at this quote, derived directly from the core academic benchmarks. It really brings it home. The assessment framework prioritizes analytical depth over superficial breadth. Let that sink in. Cambridge examiners aren't just looking for you to recognize that a filament lamp graph is an S-shape. That is superficial breadth. Any student can memorize a shape. Analytical depth means you are explaining exactly why the gradient changes. Top students use a framework like peel, point, evidence, explanation, link. So, for a filament lamp, you don't just say, it curves. You articulate that as current increases, the temperature of the filament increases. This causes greater lattice ion vibration, which leads to more frequent collisions with electrons. That increases the resistance, which causes the gradient of the graph to decrease. Boom. That's analytical depth. They are looking for a structured, logical reasoning process that works even when they throw completely unfamiliar components at you.
Moving right along to Section 2, Core IV Graph Principles.
You know, there are very distinct cognitive domains that these assessment objectives target. It's not a secret. It's right there in the syllabus. First is knowledge and understanding. That's the basics. Knowing Ohm's law. Knowing the basic shapes of your graphs. Second is the application of principles. This is where you take that baseline knowledge and use it in a brand new scenario they've invented for the exam. But look at the third bullet point. This is the VIP section. This is where the A star is truly won. Analytical depth and evidence-based reasoning. When you're evaluating an IV graph for, say, a diode, the data points on that graph are your primary evidence. It is absolutely not enough to just write, it only conducts in one direction. A thorough top-tier analysis explicitly states, as evidenced by the graph, the current remains at 0 amperes until a forward threshold voltage of approximately 0.6 volts is reached, demonstrating. Do you see the difference? You have to be an investigator. You use the evidence to prove your reasoning.
Which brings us to Section 3, the procedural framework.
Because knowing the physics is clearly only half the battle, right? The other half is the highly specific methodology required for execution. I want to talk about something fascinating here, the method mark strategy. It is defined as earning marks by demonstrating a systematic, step-by-step analytical process, even if your final calculation is slightly off. I absolutely love talking about this because it's like the secret insider playbook for maximizing your points on complex IV graph problems. Imagine you're doing a multi-part calculation question. You're asked to determine the resistance of a filament lamp at a specific voltage by reading a graph. You're stressed, the clock is ticking, and you accidentally misread a tiny microscopic grid line. Your final answer is wrong. But if you clearly showed your formula, your substitution, and your logical step-by-step math, the examiners can still award you the vast majority of the points. The process is what truly counts. The examiner wants to see how your brain works, not just a magic number at the bottom of the page.
So, how do we guarantee we get those method marks? Here is the exact step-by-step sequence recommended for tackling these problems. You should treat this like a checklist every single time. First, deconstruct the question. Underline or highlight the command words. Is it calculate? Is it compare? Is it explain? Second, extract relevant data. And please read the axes carefully. Is it an IV graph, or did they try to trick you with a VI graph? Because let me tell you, that completely flips the meaning of the gradient. Third, select an analytical framework. For written answers, that Peel framework we mentioned, point, evidence, explanation, link, is your best friend. Fourth, execute with clear notation. Show every single step of the math. Leave a breadcrumb trail for the examiner. And fifth, present with correct terminology. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's move into Section 4, Principal Examiner Warnings.
Okay, let's play a little game of Find the Flaw. We are going to look directly at the top 3 mistakes flagged by official Cambridge Principal Examiner reports. These are the traps that cost students entire letter grades. Mistake number 1, answers are too vague. Imagine a paragraph describing a resistor of constant resistance. A flawed, vague answer just says, it's a straight line. The examiner reads that and thinks, okay, so. A top-tier specific answer says, the current is directly proportional to the potential difference at a constant temperature, as shown by the linear graph passing through the origin. See how much richer that is? Mistake number 2, forgetting to check format and presentation. This means finishing a beautiful calculation and then leaving out the units, ohms, amps, volts, or completely messing up your significant figures. It's a tragic way to lose points. And mistake number 3, answers are not specific to the given context. If a question is about a thermistor inside a very specific circuit context, giving a generic textbook definition of a thermistor isn't going to cut it. You have to relate your knowledge back to the actual data they provided you.
Now, what's really interesting about this next point is that it's a massive glaring alert from the examiners themselves. Candidates consistently confuse key terminology. It is absolutely crucial to define your technical terms clearly before you start analyzing the data. For example, using the word resistance to explain a filament lamp's behavior requires demonstrating that you know resistance is the ratio of potential difference to current. You'd be amazed how many students casually swap words like power and energy as if they mean the same thing when describing these graphs. They don't. Precision in your vocabulary is treated with the exact same level of importance as precision in your mathematics. If you use the wrong word, you change the physics, and the examiner has to dock you marks.
Finally, we reach Section 5, Critical Evaluation Skills, the final plating of our MasterChef recipe.
Comparing these two approaches perfectly illustrates what examiners are hunting for when they give you an evaluation question. I want you to mentally picture a 30-second speed writing challenge right now. The prompt asks you to compare the IV characteristics of a fixed resistor and a filament lamp. A poor analysis just lists basic facts independently. It says, the resistor is straight, the lamp is curved, no flow, no connection. But a top-tier analysis, it's a completely different league. It identifies similarities and differences. It actively uses comparative connectives like whereas or conversely. And most importantly, it supports every claim with hard evidence from the data. Listen to this perfect Peel paragraph. Both components show an increase in current as potential difference increases. However, Whereas the fixed resistor maintains a constant gradient indicating constant resistance, the filament lamp's gradient decreases at higher voltages, proving an increase in resistance. That right there, that is the gold standard. That is exactly what secures the maximum possible marks.
I love this table. This deconstruct, solve, evaluate loop is essentially the ultimate screenshot-worthy cheat sheet for data interpretation skills. Under deconstruct, the explicit examiner expectation is that you are actively identifying given information from the texts and the tables. You are hunting for clues. Under solve, you are taking the problem, breaking it into logical steps, and executing it systematically. That's how we guarantee those method marks we talked about earlier. And finally, evaluate. This is so often skipped. Checking your final answer for reasonableness is essential. Think about it. If you calculate the current for a tiny little filament lamp and your calculator says 4,000 amps, you need to pause. That physically unreasonable result should be a massive red flag screaming at you to go back and check your algebra. A 4,000 amp desk lamp isn't glowing, it's vaporizing the room. It's all about questioning assumptions and making justified recommendations based on reality.
We've explored some genuinely incredible, game-changing insights today. Let's distill all of this into 3 absolute key takeaways based on everything the source materials and examiners have told us. Number 1, decode. Always decode the command words and check the axes of your graphs before you write a single word. Number 2, apply. Apply the method mark strategy by showing systematic, step-by-step working and structure your written answers logically using frameworks like PEL. Number 3, evaluate. Never be vague. Use specific evidence from the data provided to justify the underlying physics reasoning. Students who actually implement these physics strategies see an average improvement of 2 grade boundaries. But let's be real, that only happens if you practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSA to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSA and click that bell. Don't let another exam pass you by without having the best strategies in your back pocket.
I want to leave you with this final provocative thought. You now possess the exact step-by-step recipe for mastering IV graphs. You've seen the pitfalls, you know the strategies, and you understand the level of analytical depth required. But knowing the recipe and actually cooking the meal under pressure are 2 very different things. So I have to ask, are you truly ready to evaluate the evidence and think exactly like a principal examiner the very next time you sit down with a past paper? Drop a comment below with your target grade for physics and the biggest challenge you're currently facing. Our team responds to every comment. Like and share this video with a study partner who needs to hear this. Ace the Exams, your Cambridge success starts here.